So good morning, good afternoon, good evening. Welcome, everyone. We're pleased you could join us for this third installment of the Trace Training webinar series hosted by the NRC and ISL. And we have 81 users registered for this webinar, and hopefully a few more will drop in as we proceed along here. We've got about 3 hours set aside for this, and we'll have a short 5-minute break about halfway through. I did want to remind everyone this meeting is being recorded, and you'll get the meeting recording posted on NRC codes after this meeting. So I've got a few more logistical things to go over, but first let me turn it over to Chris Murray, who will say a few words. Go ahead, Chris.
All right. Hi, everyone. Can you hear me, right?
Yes, you're good.
Okay, good. Yeah, welcome, everyone. My name is Chris Murray. Many of you probably know me, maybe some of you don't, or at least my face. Yeah, I'm Chris Murray. I'm the code caretaker for the Trace code here at NRC, and I manage a development contract we have, plus that brings us training to you all, and also manage the distribution of Trace to you all. And I just wanted to say welcome and get on here to show my face. And today's topic is going to be on control system modeling and control theory, and I think that's a topic that many people have expressed interest in hearing some specific information about. And so I think this training is kind of very dense in content. When we were going through our run through a couple weeks ago, I think we even had more content than probably the 3 hours would allow. I'm guessing ISL has figured out how to trim that down a little bit. This is an important topic for modeling with Trace, and can really make or break an input model that you're developing in terms of how it's working, and how well it runs. And so learning how to build PI controllers and controllers that can control the various aspects of a simulation, help bring the code to steady state more quickly, is an important topic. And also, we constantly find or have input models and issues from people where they say, hey, I'm having this problem with this model. We don't understand why the code's giving me this behavior. And you look into it, it may be a trip that wasn't quite defined right in your model and things like that. So it is a very important topic. And so we're pleased to be able to bring this to you. I think the next training after this, we're gonna go into some relap 5 conversion will be the next one. After that, I don't think we have a topic lined up yet beyond that, but we are excited to be able to bring these webinars to you and fill a gap in training that probably has been lacking over the last 5-8 years or so. So and I'll just say that we have a great team of individuals. Lance, Justin Watson, who teaches the first is Lance Larson at ISL, and he has a lot of knowledge of control system modeling and theory. We also have Justin Watson, who is a professor at University of Florida that took a class with me a long time ago on Trace. When I was learning about Trace and joining grad school, he was in the class with me learning how to run these codes. And one of the topics is that they went into in the class was learning how to deal with these control system models. And now he's actually teaching that same course at University of Florida. So he has a real depth of knowledge on this topic as well. And then some of their other staff as well will be helping out. So that's all I have to say. And I'll turn it back over to Doug.
Great. Thank you, Chris. So this is intended to be an interactive workshop. We do want to be able to provide you an opportunity to engage directly with our trainers, and with other Trace developers and instructors and others at the NRC that have insights into the different topics that we present over the course of this webinar series. So feel free to ask questions. You can raise your hand. You can post a question to the chat. and we can take you off mute and you can ask the question verbally or you can put it in the chat, whatever you'd like to do. But we do want you to participate. There were materials that were sent out. For some of you, those just came out this morning. Apologies for some of the ones that registered more later. I didn't get those materials out to you as quickly as I would have liked. But for others, you should have received a packet of materials last week. And if you didn't get it, these will be posted to NRC codes following the webinar, along with the recording of today's webinar. So we'll have materials, and if you've already got them, you can use them and follow along if you'd like. If you'd like to just sit and listen, that's also fine. However you'd like to proceed. So this webinar is broken up into kind of two basic topics. The first one would just be an introduction into trace control system modeling, and Justin Watson will be presenting on that. And then we'll take a short 5-minute break and we'll get into control system theory. And Lance Larson will be presenting that topic with assistance from Jack Haney and Isaac Hornbeck. So with that, let's go ahead and turn it over to Justin and we will begin.
Okay, great. Let me share my screen here. Okay, hi everyone. So we're going to start today off with a brief discussion of the different components that are used to construct control systems in Trace. Then we'll get into some hands-on exercises. Everybody can hear me okay and see the slides right now?
Yes.
Okay, great. Thanks. Okay, so trips in control systems and control procedures are used in trace models for implementing safety-related control systems, for calculating analysis results, and for reaching steady state. So the first part of this webinar, like Doug said, is we're going to introduce you to some commonly used control block components and give you practice implementing control systems in a model. And then the second part will be focusing on understanding how to optimize PI controllers and reaching targeted steady state results. So some of the objectives of today are to practice signal variables, control blocks, and trips and adding them into models, understand how control systems can be used to mimic real reactor controls, practice building control systems in Snap, understand how to characterize these system response to derive PI controller gains, and practice implementing PI controllers into a system. Whoop. Sorry about that. Okay. So this presentation, I'm sorry, is there a question? No, okay. This presentation covers an introduction to control systems. We'll cover signal variables, control blocks, trips, and component action tables. Now, we're not going to cover all the slides in this presentation. They're presented here or given to you for completeness, and a lot of this information was covered in the first webinar, but instead, I'll cover some basic properties of these individual components, and then we'll get right into the exercises to go through the hands-on training. Okay, so in an operating reactor, the electronic and mechanical systems are put into place which give the operator manual or automatic control over the system's behavior, right? Well, the trace control procedures give the code user the same level of control over their computer model. It allows the user to model automatic control of regulating hardware as well as abnormal hardware behavior. So an example of abnormal hardware behavior would be opening a valve to simulate a pipe break. Okay. The control system implemented into Trace is general and flexible. The user has to really think about how they're modeling the control specifications to construct these control procedures. But in general, it's often just used to control the behavior of thermohydraulic components. For example, changing a valve flow area, or maybe using it to set boundary conditions like pressure, velocity, mass flow rate. maybe set reactor core programmed reactivity or power. So there's a lot of different uses for these control systems. Can also be used to calculate convenience output variables like pressure drops, collapsed liquid levels, and heat transfer rates. And part of the webinar today will be doing some of that. So there are 4 basic building blocks of a trace control procedure. They are signal variables, trips, control blocks, and component action tables. A signal variable are basically system parameters that have real values that a user can select, basically the type of a variable and the location from the model that they want. So for example, if you want pressure or temperature from a particular thermohydraulic component in your model, or maybe know the flow, the valve flow area of a particular valve in the model, you would use a signal variable to grab that data from a specific location in the model. And then that's used in control blocks, trips, or component action tables to perform some action on the model. Trips are just logical operators that test the current value of an independent variable against a set criteria or a set point. And that set point then will determine the value of a trip. Trips typically have 3 different states: on forward, off, and on reverse. And they have a numeric value associated with each. So on forward is a 1.0, off is 0, and on reverse is minus 1.0. Control block is nothing more than a mathematical function that operates on 0 or more inputs. So it typically takes inputs from signal variables or other control blocks, performs some mathematical manipulation on that input, and then is either sent to trips, component action tables, or operates directly with the model itself. Then finally, the component action table. This provides a means for modeling the adjustable hardware action of a component. These are essentially just lookup tables for which the response of some key parameter may be determined as a function of an independent variable. So while we're presenting component action tables here as part of the trace control system, when we're implementing component action tables, they're actually input with the component itself, not within the control system. But they're typically initiated by a trip and then use control block output or signal variable output to control the independent variable function of the table to determine the hardware action. So if you look at this diagram, you can kind of see the general flow. We get signal variable data from the model. We perform some function on it. And then we have some hardware action that feeds back into our model. Okay, so that's the brief overview. So let's now step into one of the exercises and see how we can actually implement these concepts into a model itself. So let me share here the first exercise. This first exercise that we're going to go over can be located in the Trace Webinar 03 Materials Directory, subdirectory Exercise Instructions, and is titled Trace Control System.pdf. If you open that PDF, you'll see a step-by-step instructions for this first exercise. This exercise itself is broken up into 2 parts. The first part is a simple heat transfer rate calculation in a model, and then the second part will be controlling some fills for the makeup and letdown flow using a simple proportional controller. So part 1 of this exercise here, we want to calculate the heat transfer rate in a single steam generator tube bundle. So we can do that using simple balance here for our enthalpy and pressure difference between the outlet of our steam generator tubes and the inlet of our steam generator tubes. To do this, we'll need the mass flow rate, liquid internal energy, liquid density, liquid velocity, and pressures at both the inlet and outlet locations of our steam generator tubes. Some of this information is cell center or cell volume data. So internal energy, pressure, and density are all cell volume data. And some of the data is going to come from cell edge values. So mass flow rate and velocities provided at the cell edge. We're also going to make some assumptions. The first assumption is that all the flow in the primary side is liquid, which is fine assumption for normal operation. If you want to do the same calculation for two-phase flow, you would have to add in then all of the variables for the vapor phase as well as the liquid phase. And you can do that, but we already have a fairly dense training for you today, and so we've simplified this model quite a bit for this purpose. We'll also assume that the liquid mass flow rate out of our steam generator tubes is equal to the inlet mass flow rate. And we're going to assume that the tube bundle outlet and inlet are at the same height. So here you can see in this diagram, we have our model of our steam generator tubes. In the model that we're going to look at today, they model the whole primary side using one component, one thermohydraulic component. It has 18 cells. Cells 3 through 16 represent the tube bundle itself, and that's what we're going to calculate the heat transfer rate for. The model also includes heat transfer in both the inlet plenum and outlet plenum, but for our purposes, we're going to ignore that heat transfer for now. So with our assumptions, our heat transfer rate equation, we can rewrite it in this form, and we can write it in terms of a simple internal energy difference, pressure difference, and velocity difference times then a single mass flow rate. Now, if we rearrange this equation such that we're now pulling the data from each of our cells, we can write it in this form where we have now the internal energy difference between cells 16 and 3, pressure difference between cells 16 and 3, and velocity difference between now cell edge 17 and edge 3. And then in our model, we'll just use our inlet mass flow rate at cell edge 3 as our mass flow rate. The objectives of this are just to understand how to use the signal variables and control blocks to construct equations that provide us some useful information. And we're also going to add a plot to the animation view associated with this model. We're going to do this in 4 basic steps. The first step is to create a new view tab to actually create our heat transfer calculation in. Then we're going to add the heat transfer equation to that new tab. So adding all the signal variables and control blocks in order to construct this equation. Then we'll run a steady state model that, or we'll run a steady state calculation for 1,000 seconds. Once that's done, we'll add a new strip plot in our animation mask to view the results. Okay, so you can follow along with the detailed instructions in the PDF or try to follow along with me as I walk through. We're going to go through all these steps together. So if you haven't done so already, go ahead and start up your model editor and then load the PWR steady state model that's included in the materials package. So we can see an open model in the Trace Webinar 3 materials directory. You should see in that parent directory, you should see a PWR steady state.med file. We're going to go ahead and open this file. Now, this exercise is assuming that you've already gone through all the steps to get a snap set up with the configuration tool, and you have a trace version 5 patch 9 available for this already. Okay, this model, if you were at the Trace Webinar 2, is based on that same PWR model. If you're not familiar with this model is a full 3-loop pressurized water reactor. It contains all of the primary system components as well as most of the secondary components and safety systems. So it has high pressure injection, low pressure injection, has modeling letdown and makeup flow, and everything from the secondary side main feed water to our steam generators through the steam line up to basically the turbine stop valve. So it's a reasonably detailed model, and it also has a reasonably detailed control system that's representative of a model of this type. And this model was originally set up to do a small break loca. While we won't be necessarily dealing with that transient today, we did do that in the second webinar. If you click on the control system tab, you will see that there are a lot of control systems in this model. We're not going to be interacting with a lot of these today, but you can see a lot of details in the control systems here. There are also additional views in the navigator window. If you go to the view, there are different control system views available as well for you to look at. Again, I've closed most of these so that we can concentrate on the tabs that are most relevant to this exercise. Okay, so the first thing we're going to want to do is add our new view tab to our model. Go ahead and under the navigator window, right-click on Views and select New. When you select New, a new window will appear. We can give it a name. Let's give this name SG Heat Transfer. Okay. And then you can see that you can change some of the properties. We're going to leave most of these the way they are, but we are going to change the canvas size. This will give us a little bit more room to place our control system or our control procedure in. Let's go ahead and change the height to 1000. And when we do that, you'll see that our view window here has grown a little bit larger for us to use to place our control system. Okay. So we want to start putting in the signal variables and the control blocks for our equation. If you don't remember the equation that we want to program and where we're pulling all the data from, we're going to make it easy here. We're going to actually insert an image of our equation into our view to help us with constructing this. So we can go up to our component selection tool here at the top of the snap window. And under animation, you'll see an option called image. Go ahead and click on image, and then click near the top of our view window, and you'll get this sort of generic light bulb icon. If we click on that, you'll see it has some properties, has some dimensions. But also under image, we can select the image we want to insert in its place. So if you click on the three-dot button, a new window will appear and it says select image. Click on the selection button and then navigate to the location where you've stored the webinar 3 material. And under exercise instructions, you'll see that there's a file called heat transfer rate PNG. Go ahead and select that file and then click open. Then OK. That will insert an image of our equation that we're going to create the control system for in our view. So now this helps us determine where exactly we want to pull information from. Okay, so when we want to start adding control system components to our model, the first thing we want to do is come up to our component selection tool, and you'll see that there's a control systems option. And here you'll see that there's trip data, control blocks, and signal variables. Let's first start with trip data. Well, we're not going to be using trips in this particular exercise right now. Let's go over and just take a look at what are all the options when we add those to the model. So if you click anywhere in your view after selecting trip, you'll see it inserts a trip that looks like a triangle, right? Okay, you can give it a name and a ID number. The ID number has to be a unique number. If you're ever need to be reminded of what values are valid for trips, you can click on the little question mark here, and you can see that trip ID needs to be between 1 and 9,999. Now, usually trip IDs are positive. When they're positive values, they're only evaluated during transient calculations, which is very nice because you can set up your whole control system and you can have trips that are initiated at different set points on parameters. And when you're running your steady state, you don't want that to be evaluated. You only want it to be evaluated in subsequent transient runs. So you can actually add all your control system to your steady state model itself, and it won't be evaluated. However, there are times when you want your trips to be evaluated during steady state calculations, and if you make the ID value negative, it will be evaluated both for steady state and transient calculations. The next input is your set point data. You click on that expansion tool, you'll see that it has a trip type already selected. There are 11 trip types in trace. The first 5 are traditional trace type trips. 6 through 11 are relap style trips. But the most common ones used are types 1 and 2. The primary difference between these is how it operates. So type 1 is set off when set point 2 is crossed and turned on forward when set point 1 is crossed. Type 2 is the opposite. So it is set on forward when set point 2 is crossed and set off when set point 1 is crossed. Now, the nice thing about trace trips is they include this deadband here between the two set points, which makes these trips very useful and flexible and really are capable of really modeling real reactor control trips. Okay. The other types become more complicated. They have more set points. We're not going to go through all of them today, but you can see that how they vary here when you're selecting your type of trip that you want to use in your model. Okay. You can specify the input source. If you click on the selection tool here, you'll see that it'll have a listing of every control block or signal variable that's defined in your model. And these, you can just simply select the signal variable or control block you want as your input source to your trip. And then there's some other input data here as well. Okay, let's talk about control blocks next. So a control block, like I said, is a mathematical function that works on some input. So we can select a control block again by going to our component selection tool, control systems, and control blocks, and then clicking anywhere in our view window. When you do this, you'll get a listing of every control block that's available in Trace. And one thing you're going to see is that it has a category, it has a unique number, and then the type of control block. You can actually organize these by just clicking on the header of the column, and you'll see that control blocks are basically categorized based on their function. So you have arithmetic, so things like divide and sum. You have calculus, so your derivatives and your integrals. Control blocks, which you'll hear more about later, so things like PI and PID controllers. Logical, manipulation control blocks to do things like absolute values, time-related control blocks, and then finally trigonometric functions. So if we click on one of these, let's do type 14 divide. So find control block 14 divide, say OK. We click on this control block, it'll enter it into the model. And the first thing we can do is give it a name and a control block ID number. The control block ID number also has to be unique, and it must be negative. So all control block numbers are negative. The type is shown. We can always change the type of a particular control block by clicking on the selection tool to pop up our menu to select the type. We'll leave it at divide for now. And then it has some input for us. So the first thing is gain. Gain is a value that multiplies the output of every control block. So if you have this is convenient because if you have like a factor that's multiplied by something, often it's a 1/2, you can actually change the gain to 0.5 and it will multiply anything that it's calculating here by that value. So it's very convenient for adding in constants sometimes when you have a parameter multiplied by a constant. And we'll see that in action a little bit later. You have your minimum and maximum values, and then there's constant 1 and constant 2. Now these perform different functions based on the type of control block. If you click on the question mark here, you can see the constant 1 is used for not all control blocks, but a lot of them. And they take on different functions or meanings based on the type of control block you're inserting. Constant 2 only has a functional value for about 5 of the different types of control blocks here. However, for all others, when allowed, you can actually insert a value that's non-zero as an initial value for the output of that control block. So that can come in handy sometimes if you want to initialize your control block output and it's not used for some other function. And then finally, we have our input connections. You click on the expansion button here, you'll see that there's input for your numerator and your denominator. If you have your numerator here, you can click on the selection tool And again, it'll show you all control blocks and signal variables in your model, and you can select the one you want that represents your numerator here. One thing I wanted to point out here specifically, and you can do the same thing for your denominator as well. One thing I wanted to point out here with the divide, notice that it gives you an N and a D on the view here. And this stands for numerator in your denominator. So we can use select our inputs using this menu system, or we can use the connection tool to connect directly to these, and this indicates which input is the numerator and which is the denominator. The other thing is that if you're using a divide block and you come in and you look at constant 1, if you notice that 14, the divide, if we set constant 1 to a non-zero value, we can actually give it a constant numerator. So if you want and you have a constant in the numerator portion of your division, you can actually input that here. You don't need another control block or signal variable to give you that data. You can actually input it here and it'll be a constant numerator for you. Okay, finally, let's talk about signal variables and then we'll start building our equation. So let's go back up to our component selection tool, control systems, and signal variables. Click on that. And again, click anywhere in your view window and you'll get the select variable type window pop up. There are 134 different types of signal variables that you can get from your model. Again, they all have a unique number and are categorized by sort of their function. And if I click on category here, you'll see that it's now reordered them into just different categories. The first one is general signal. So things like problem time are categorized under that heading. There is a very useful signal variable called generic signal variable here. This really gives you access to any trace parameter that's in the code that you don't have a pre-built signal variable for. The issue here is you really need to know the internal variable names of trace to use this effectively, but if there is a parameter in trace that you want the value of and you don't see a signal variable for, chances are you can get access to it using this generic signal variable. So that can be a very useful and powerful input. And then again, it has component-specific signals, so things like pump motor torque, turbine torque, etc. The volume signals, so if it's a cell volume value, things like pressure, liquid temperature, densities, etc. You'll find them here listed or categorized as a volume signal. We also have the edge signals, so your mass flow rates, your velocities. One thing I wanted to point out here is notice that we have X, Y, and Z components for all of these parameters. And this is really meant for 3D components. If you're grabbing the vapor velocity or mass flow rate for a 1D component, you can select any of these. They will all provide you with the same value. So it doesn't matter for 1D components. But for 3D components, it will take on a different value. So we have heat structure signals, control signals, and then power signals as well. So things like core power, total reactivity, etc. Okay, so let's go ahead and let's find signal variable 82. That's liquid internal energy. We'll go ahead and we'll select that and we'll put that into the model. One thing that I didn't point out before, but notice when I input the signal variable, the sort of icon for it changed, right? It's a rectangle with curved corners, where a control block is a rectangle with sharp corners. This helps you visually determine very quickly whether something's a signal variable versus a control block. And as we saw with the trip was actually a rectangle, right? So let's go back and look at the signal variable input and see what we can input here. So again, we can give it a component name, and it needs to have a unique ID. One thing that Snap will do automatically is find a unique ID that doesn't exist in the model already and assign it that value. You can use the Snap assign values where you can change it. We're going to change a lot of the values in this exercise here in a minute. But Snap will actually pick a value that is unique in the model, so you know it doesn't conflict with any other signal variables that have been defined previously. Again, we can define the parameter type, and we could change it if we want to. And then the rest of the input is just the signal itself, so where we're getting the signal, the hydraulic component and cell, and the behavior mode. Let's take a look at that really quick. So there are 6 different behavior modes that signal variables can potentially have. Not all signal variables have all 6 of these functions, but most of the ones that we talk about today will have these 6 functions. The exact value, which gives you the exact value of that parameter for that cell location or edge location. We have time difference. Time difference will give you the difference in that parameter at the current time versus some previous time. Cell difference will give you the difference in a parameter over between 2 cells in a single component. Minimum and maximum will give you the min or maximum value of that parameter over a range of cells. And then volume average gives you the volume average of a parameter over some range of cells in a single component. Okay, so for this one, first thing we want to do, if we look at our equation again, we'll see that we want the difference in our internal energy between cells 16 and cell 3. So we can actually select cell difference for this first term in our equation. It's the liquid internal energy. We already have that parameter type selected. Let's go ahead and click on cell difference. And while we're here, let's give it a name. So let's call this one SG1 delta internal energy. Okay, and we're going to give it the ID number 20. I've looked at the model and I know that that is unique, so we can give it the number 20. So the last input we need is our signal variable data. So if we click on the expansion button here under property view signal, the first bit of information it's going to ask us for is the hydraulic component. So if we click on the selection tool, again, it gives us a full list of all the hydraulic components in our model. For us, we want the primary side steam generator, a pipe that represents the steam generator tubes, and that's pipe 105. So if you scroll down to pipe 105, you'll see that in the component description, it is steam generator 1 primary. So this is our hydraulic component that contains our steam generator tubes. We can say, okay. And then the next thing it's going to ask us for is our first cell location and then our second cell location. Looking at our equation, we may be inclined to go ahead and put our first cell location at cell 16 and our second at 3. And we can do that. However, the cell difference functionality of the signal variable actually subtracts the lowest valued cell from the highest value cell. So if I put 16 as the first and 3 as the second, or I put 3 as the first and 16 as the second, it will always give me the same value because it's always going to subtract cell 3 from 16. So that's okay as long as we know that, right? So we can go ahead, you can leave it in any form you want and just select OK here. But it's important to note that this output is going to give us the internal energy in cell 3 minus 16, which means our sign's going to be wrong for this equation, right? So we're going to have to fix that at some point. And there's several different ways we can go about doing it. I'm going to show you one way in a little bit. So just keep that in mind that our sign is not going to be correct for this first term in our equation. The next term we want to go and start writing the control system for is our pressure divided by our liquid density at the outlet. Okay, to do that, we need two new signal variables, one for the pressure at the outlet and one for the density at the outlet. If we go up to our component selection tool, one of the things you'll see is when we select a new component, right, the icon to the left of it changes. That says, okay, we still are on signal variables. So we can just click that icon and that will give us the ability to input a new signal variable. So let's go ahead, click on that, and then click on your view window anywhere under our first signal variable. Now we're going to want to find our pressure. Our pressure is variable 20 or number 21. So if we scroll up to signal variable 21, we will see that that's pressure. We're going to go ahead and insert that into our model view. And in the properties view, let's go ahead and give that a name, and we'll call that SG1 outlet pressure. We're going to give it signal variable ID 21.
So earlier you indicated that that you knew these were unique names, numbers that they hadn't been used. How would you show, like, how does a user know if it's free?
Well, okay, so one of the ways that they can do it, it's a good question, is under the navigator window, you will see a listing of all of the trip data, control blocks, and signal variables, right? And you can look at this list and see which ones are available. And if you look up here, we can see that we don't have any signal variables valued in that range. So we should be good.
And they do come in this list in order, so
Yeah, they can.
so you can see where the gaps are in this particular list. It's a little more difficult with controls. Another way to do it is with the find menu. You can try and find items and it'll show you the list of, like, if you look for something with 20, you could see whether it was available.
Yeah, I could right click and do actually find here and just search for 20 and it'll show me all components with 20 in it. There is a pipe 20, a trip 20, but they won't conflict. There won't be any signal variable 20 as well. Okay, good, thanks. Okay, so we've got our pressure. We need to now get our signal variable. In this case, since we're dividing by the liquid density, we're just going to use the exact variable. So let's go to our signal variable input in the properties view and click on the expansion. Again, we're going to select pipe 105. So all the signals are going to come from pipe 105. So we can quickly go through this, select 105, say OK. And then it will ask for a single cell location now. In this case, we're going to put in cell 16, select OK. Okay, so that gives us our pressure in cell 16. We need the density in cell 16. Now, we can come up here, click on our signal variable icon, insert again, and liquid density is going to be type 72, or 75, sorry, 75. So find signal variable 75, liquid density, say OK. Again, we can give this a name, call it SG1 outlet density, and we'll give it another unique number, 22. Again, we're going to use the exact value, and we'll do signal variable here from pipe 105. Say OK. And again, we're going to give it cell 16. Okay, so now we have our pressure and our density at the outlet. We need to do the division. We already have our division block from earlier. If you didn't insert a division block into your model, you can always come up to the component selection tool, control systems, control blocks, and then find control block type 14 and insert it into the model. Okay, we're not going to change the name of this one. It's not important for this exercise to give it a name, but we will change the number. And again, we're going to change this one to control block -50. We'll leave it at divide, and we need to add.
And for what it's worth, control block numbers are always negative, so.
Yep. Yeah, I had mentioned that earlier, that they must always be negative. Okay. Again, we can go through and do the input connections in one of two ways. We can click on the expansion button here and then select the component. This takes longer, is a little more cumbersome. The quicker way of doing it is using the connection tool, which is at the top of the view window here, and it looks like sites. So if we click on the connection tool, you can click on the handle to the right of our pressure signal variable, and then click or go to the control block -50, and you'll notice that as I get over the diamond next to the end, the site turns blue. It says I can connect there. If I click again there, that will connect our pressure to our numerator input. This is very similar to connecting thermohydraulic components in our model, right? To connect the density to the denominator, again, click on the little handle to the right of the density or signal variable, and then the diamond next to the D on our division control block.
And for what it's worth, you have to click on the circle ones first before you click on the diamond. You couldn't do it the opposite direction. You can't connect from the control to the signal variable.
Right. Yeah, you always go from signal variable to control block. Okay, so this simple system will give us our division of our pressure with our liquid density. Okay, now we need to do the same thing for the input, and we can follow the exact same procedure to insert two signal variables and then a division block, or we can take a shortcut and just copy and paste these. So we can highlight all these by just simply left clicking and dragging a box around uh, the components, right? And notice they'll be highlighted. If we right click and say copy, you can left click, and there's two options. One is paste and paste special. In this case, paste will try to paste an exact copy and it won't work. This is more for copying from one model to another. If we paste special, you'll get a new menu up here and it'll try to automatically offset the numbering in this model so that you have, again, unique numbers for your components. We can just leave this at offset component numbers by 1 and say OK, and it'll make a copy of all of those control systems. Okay, again, we have our pressure, our density, and our division block. We now need to convert these from using our output conditions to our inlet conditions. So the first thing I want to do is I'm going to change the name of this, the pressure, to the steam generator 1 inlet pressure. And I'm going to give it a new number just so they go in order. And I'm going to duplicate one, but we'll fix it here in a minute. So I'm going to call this one 23, ID 23. And we need to now change it from cell 16 to cell 3. So if we click on our expansion tool here, we can simply just change our cell number to 3 and say, OK. We can do the same thing for our density. We'll change our name from steam generator 1 outlet to inlet. We're going to change our number to 24. And we're going to change the signal variable location from cell 16 to cell 3. Okay, and once you do that, now we have, for our second term in our equation, both the outlet and inlet divisions. So the next thing we have to do is subtract them. So again, we can go and add in a new control block using our component selection menu. Click here in your view window, and now we have to find subtraction. Okay, so
Can you sort the type column? Click
yep,
at the top
that's
of the
exactly
type
what I
column.
was going to do.
Oh,
So
okay.
we're going to sort via the type, and if we scroll down, you can see the type 54 is subtract. So we can go ahead and select that one, say OK, and it inserts into our model. Again, here it has indicators on the control block icon to show which is the plus side of the subtraction, so the first value, and then a minus for the second value, the value you are subtracting from the first. Okay, again, I'm going to change our control block number to minus 52 to just be consistent with our numbering. And then we can simply connect our control block outputs to it. So using our connection tool, we're going to connect control block minus 50 to the plus side of control block 52. And we'll connect control block 51 to the minus side of control block 52. And that should subtract the outlet from the inlet in this second term of the equation. So this gives us our full second term of our equation. The next thing we need to do is our velocity difference. Okay, so again, let's go and insert a signal variable to calculate our velocity at cell edge 17. You can do that by coming back to our menu, selecting signal variables, and we'll just add this underneath our other signal variables. So we're looking for signal variable 39, which is fluid velocity across the x-axis. Again, we could select Z or Y, it doesn't matter, but we're going to select x-axis here. Go ahead and add that to our model. We'll change the name of this to steam generator 1, SG1, outlet velocity. And we're going to give the signal variable number 25. Okay. Again, we're going to use the exact value for this. And we're going to connect this to pipe 105, cell edge 17, right? So now we're at a cell edge value, so we want cell edge 17. Say OK. Now the next thing we have to do is actually square this value. If we come into our control blocks, we can go ahead and insert a new control block into our model. And if we look, we're not going to find a control block to do a square, right? There's square root, there's subtract, there's step, there's no square. So there's a couple different ways that you can square a value. We could create a whole nother copy of that signal variable and multiply those two signal variables together, or we can do just multiply the same signal times itself, and that's what we're going to do. So what we want to find is the multiplication block here, control block, and that's going to be control block 39104. So some of these control blocks you'll see have more than one number associated with it, and I think a lot of that comes from historical, where they had two different multiplies that applied to different used different forms of multiply, and they've just combined the functionality now into one. Same for some that historically, if you had a type 3, 56, 57, 59, or 103 sum, they all now have the same functionality within the SNAP framework. So we can go ahead and just select multiply here, and we'll add that to our model. Now, if we want to square our signal, all we need to do is first go to our connection tool. Again, we're going to click on the circle handle to the right of our velocity and connect it to our multiplication block. Notice it says that it's the first input, x1. If we want to do that again, we can click on the circle handle and go over to our multiplication again and click on the area indicated by this X when we see the blue dot. Now you'll notice that we have two inputs to this from the same signal variable, x1 and x2. So it'll multiply them together, effectively squaring this value. If we wanted to cube the value, we could make yet another connection. But for now, we just want to square it. So now we have our velocity at cell edge 17 squared. Let's now do the velocity at cell edge 3 squared. Again, we can do this simply by selecting both of our components using by dragging a box around them, right-clicking copy, and do a paste special. Again, let it offset. Now we have a new signal variable and a new multiply block. So right now we don't have to change our signal variable number because it gave it 26, but we do want to change the name to inlet, and we need to change the location. So now we want to change this to cell edge 3. So if we click on the signal input expansion, we change the 17 to cell edge 3. Say OK. Now, to be consistent with the instructions, we can change these control block numbers to 53. We want for the first multiplication and 54 the second, just to be consistent with our numbering. Again, we have to subtract these for our third part of our equation. We already have a multiplication block here. We can simply copy that and do a paste special. Move this down and use our connection tool to connect our control block 53 to our control block 55 plus side and control block 54 to our control block 55 minus sign. Now that gives us the subtraction of our squared velocities. We have to add in this 1/2 here. Now remember I said the control blocks all have a gain that multiplies the output. So we can take care of that 1/2 here by simply coming to our multiplication control block and changing the gain from 1 to 0.5, effectively multiplying the subtraction times that 1/2. We hit enter. And now we have all three of the terms inside the square brackets. The next step is we have to add all of them together. We can add them by adding a sum block. We can use our icon since our control blocks are already selected here to insert a new control block. Put it up here, and we want to find sum. So look for control block 3, 56, 57, 59, 103, or sum, and go ahead and select it. Okay, you can put this here to the right of our other control system, and we can simply sum these by connecting each one of these, either the signal variable or the control blocks to our sum using the connection tool. So let's go ahead and do that. So let's first connect our difference in our internal energies to our sum. So click on the handle and bring it over to the X area of the sum block. Go ahead, click there, and they'll see a connection. Next, we're going to connect control block 52 to our sum. And then finally, control block 55 to our sum. Okay, so now we have our sum control block. Let's take a look at this. Notice that when we connected things, it gave it a little x1, x2, x3, indicating the order of input, but then there's a w equals 1.0 for each of those inputs. So the first thing we should do is change our control block number to something that is in line with our convention. So we're going to do a minus 56 here. And then let's look at what these W's represent. So if we come down here to our input connections, and click on the expansion button, what you're going to see is that there's a listing of each of our inputs, the source, and then the weight associated with it. This weight comes in handy, especially if you're creating a function and you want to weight the different components differently. We're going to use this for a different purpose for this example. Remember that I said that our difference in our internal energy has the wrong sign. We can simply change the sign of this by changing this weight value to minus 1.0, right? And that will fix our sign problem with our internal energy and give us the appropriate sign on our output. And you can see that our weight changed to minus 1.0 in our view here. Okay, so now we have all of the terms added together within our square bracket. The last thing we have to do is add in the mass flow rate and then multiply it times that sum. So let's go ahead and add in a new signal variable to get the mass flow rate here. And that's going to be signal variable 33. Yes, 33. So liquid mass flow rate across the x-axis. Find signal variable 33 and enter that into the model. Again, we can call this steam generator 1, inlet mass flow rate, and give it a signal variable ID number of 27. Again, we're going to use exact value as our behavior mode, and the signal is going to come from pipe 105. Find your pipe 105, cell edge 3. Say OK. So the last thing we need to do is just multiply these together. We can copy one of our multiply blocks, or we can insert just a new control system or control block here for multiply. Again, that was type 39 or 104. Go ahead and add that to the model, and we can simply connect these by clicking on the handles to the right in our control block. Once you have those connected, let's do one last thing and change the control block number to minus 57. And that's it. So now we have a control system that models the equation above. The first thing we want to do at this point is save our model. It's often good to save your model periodically. And the next thing we want to do is check to make sure that we don't have any errors in our model. So we can do that by going up to Tools, Check Model. And when you do that, you should see no more warnings or errors. You may have some notes here. Just ignore the notes, but you shouldn't see any errors. If you do have any errors, you'll need to go back and correct them before proceeding to running the steady state calculation. But hopefully you don't have any errors, and we can now actually go and see what results we get from this. Okay, to do that, we're going to go ahead and run a steady state calculation. This model's already set up to do that. We can click on the Job Stream tab at the bottom of our view window, and you'll get your job stream view. Now your trace here, first you may have to edit any of these, you'll have to unlock your view. So if you click on the green lock That'll unlock the view. And the first thing we're going to want to check is to make sure that our trace executable is set up correctly. And notice here, it's red, which indicates an error. And we're going to have to now attach to the correct trace executable. So in the properties view, you'll see trace is red here. I'm going to go ahead, click on the selection button, and change my trace version to version 5.0 patch 9 and select OK. The second thing we want to do is actually attach this to an animation. So in the same properties view, the animation is disabled here. Let's click on this square box to enable the animation, and it should automatically say PWR animation.med. If it doesn't, you can click on the selection tool here, navigate to the directory where we have the Trace Webinar 3 materials saved, and it should be in the parent folder called PWR animation.med. Say OK. The rest of the options we can leave alone. And now we're ready to run the steady state calculation. So we can go ahead and lock the view again and click on execute in this job stream to submit our job. Go ahead and say submit to local. The calculation should start in your job status tool. It'll do some initialization. The animation model should open and then ask you to resume your calculation, PWR steady state. Go ahead and click yes. As the calculation runs, you should see some plots here. You should have some more views at the bottom. If you only see control system view plot, you can open the other model. Maybe steady state plots here. Open these if you would like. It's going to take a couple minutes for this model to run. Let's take a short break while the model runs, and we'll resume in about, say, maybe 5 minutes or so.
Yeah, just one thing
Yeah.
while it's running. If you go back to the model where we calculated the v squared term, it's worth noting there is a raise to a power control that if you and it's named funny, so it's not obvious. Right now it's called exponential. I think we'll probably have that changed. But if you yeah, if you you'll have to unlock it so you can, but if you unlock the view, let's see, can you unlock the view right now?
Oh, unlock the view.
And then go choose your controls and go put in a new control block.
Okay.
And if you it's 60 is it says exponential. It's not really exponential, it's raised to a power. And if you hit OK, you'll see it has power, and you can put constant, that like the constant one could be set to 2, and then you could plug in your velocity, and that would give you a square. You also have the option of putting another block, like one block being your power and one block being your value. But often you just want to set constant 1 and have your input, either velocity or something to square it.
Yeah.
Okay, that's it.
Okay. Let me see something here. I had an issue with my calculation here. Let me. Okay, mine finished running. Hopefully your time or your calculations finished running as well. So let's go ahead and see how we can look at the new control system information. So one of the things that I could do is simply open up a PT plot and plot the control block variables, or I can add a new plot to our animation file and just look at the results from our steady state calculation. So if we click on the Control System Plots tab under the Animation view, should have your animation open already if it just ran. You'll see that there's an empty space. Let's go ahead and create a new strip plot for our control system. So under the component select, you'll see that there's a menu item for graphs. We can come down to the menu, expand that to strip plot. Let's click on that and click anywhere in the open area. So there's a lot of different customization you can do to our plots. We're going to just do a little bit here today. The first thing we want to do is select our plot data. So if we click on the expansion tool, we need to specify the data source. So click on the little selection tool and click Master PWR Steady State. And then we need to tell it what data channel we're going to plot. So again, if we double click on that, we'll get a little selection tool. Pop that up, and it gives us all of the variables that are available to be plotted in our model. We want to find control block 57, so CB57. We scroll down approximately around halfway, a little less than halfway, you'll find control block 57. Select OK, and then OK again. You can change the axis scaling. We're going to leave everything the same here. We're going to add an x-axis label. Our x-axis is going to be time and seconds. We'll add a y-axis label, call it Q in joules per second, units. You can change the axis label fonts. Maybe you want to change it to dialogue. So if I just highlight the font and I can start typing and it'll automatically pick it. So find dialogue, change it to, let's say, 12. We'll leave the major text font at monospaced, but we're going to change that to 12 as well. The background, it's set to black. We want to change it to white, so we can use our little color palette selection here, change it to white. And then we want to change the independent base value here to 1,000 since we had 1,000-second steady state calculation. Okay, now to populate our plot with data, all we need to do, since we already ran the steady state calculation, is click the rewind button at the top of our snap menu here. That will rewind the calculation to the beginning and then hit play. And now you should see a value of our heat transfer rate being plotted on our plot. The value is negative because we're extracting energy from the primary side. And a lot of people ask, well, how do I know that that value is correct? Well, you can verify that several different ways. One of the ways is part of an additional exercise that you can do on your own or a follow-on exercise to this, and the instructions are in the walkthrough instructions. One thing you can do is that the energy extracted from the steam generator should equal to the total power being input to the system. So you can simply create a new control system or control procedure for each of the steam generators, add them together, and compare that value to the total energy input. And that's sort of what the follow-on exercise tells you to do. When you add them together, they should match the total energy into the system. If they don't, then you may have to figure out why. And I'll give you a little hint, they won't exactly match, and it's because we didn't model all of the heat transfer in those steam generators. So think about that and think about adding or modifying the control procedures to include maybe some additional cells to make that calculation more accurate. But that concludes the first part of our walkthrough. The second part involves actually adding a simple proportional control system. Let me stop sharing here and share procedure for this. So this is, again, in our control systems exercise document. Down a little further, here we want to add a simple proportional controller to control our makeup and letdown flow based on the pressurizer liquid level. Okay, so we're going to add a small control system in our model that calculates the error in our pressurizer level based on the current level minus some target level. And then based on that level, so if the level's decreasing, we want to add 55 kilograms per second. If it's a minus 0.1 decrease in our liquid level, so we're going to turn on the makeup flow to add inventory back to our primary side. And if the level's increasing, we want to remove liquid inventory from our primary side, so we'll turn on letdown flow. Again, the objectives of this are just to practice adding signal variables and control blocks, and the modification here is now we're going to drive some hydraulic components based on that output. Okay, we're going to do that in 3 fairly simple steps. We're going to create a proportional controller. Then we're going to run a short transient to determine if the control system is working properly and examine the results, right? So this walkthrough should be relatively quick and much shorter than the previous one. Again, all the instructions are here, but let's walk through it in the model. Okay, so let's go back to our trace model. And we want to reopen our PWR steady state model. So you can just click on it. It should already be open in the model editor. You can just click on it here. All of this walkthrough is going to be done in this tab down here called Makeup Letdown Control. So if you click on that tab at the bottom of the view window, you'll see that the model's already kind of set up to do this problem. Okay, we're going to run this, we're going to do this via transient calculation. So the first thing we want to do is start editing our transient restart calculation. So in the model or in the navigator, we want to find the cases input, expand that input, and click on the PWR transient small break logo. We're going to start editing this restart case by clicking on the Restart Model Expansion tool. Notice your editing mode should be in graphical. Okay. Go ahead and click on that expansion, and that will start the model or open it up for editing our restart calculation. We want to do all the modifications here for this example. Okay, so the first thing we need to do is calculate the normalized pressurizer liquid level. Now, upon examining our previous control system, one of the things you will notice is that it's already calculated for us. So the normalized pressurizer level is calculated based on the upper tap pressure and the lower tap pressure difference, and is normalized to the maximum pressure difference if the pressurizer is completely full of water. And this effectively gives us the normalized level based on the total height of the pressurizer, or the total pressure difference of the pressurizer. So we can actually just use this directly in our control system. So if we click on the makeup and letdown flow control tab again, we can actually insert that control block in here so we can see it in this view. To do that, you want to go to the navigator window, click on Control Systems, Control Blocks, and that was control block 406. So if you scroll down and find Subtract 406, and when I click on it, you'll see that it says Normalized Pressurizer Level. That's exactly what we want. To add it to this view, just right-click on the control block and say Add to View, and we're going to select Makeup Letdown Control. When we do that, that control block should appear in our view. Doesn't modify it or anything, just displays it in this particular view. Okay. The next thing we want to do is add in our normalized target level for our pressurizer. When we want to add a constant value, like here, this is set to a constant value right now. If you look at this model the way it was originally configured, the makeup and letdown flow are being driven here. If we look at this, they are type 11 fills, right? Type 11 fills just basically says that we're going to use our signal variable input to drive our flow of our fill. Basically takes whatever signal that's input in and replaces the total mass flow rate with the slip value equal to 1 as our fill mass flow rate. Right now, the makeup and letdown flows are being driven by a constant value here, which is set to 0. So they don't do anything, right? They're disabled. We're going to remove that and actually drive them by our simple proportional controller. So again, we want to insert a constant control block. So if we go up to our control systems input, click on control blocks, add this control block number 9 is a constant, right? It's just a constant value. So let's go ahead and click on that. We'll enter that into our model and place it somewhere under the normalized target level. We can give it a name. We can call it norm PRZR target level. And we're going to change the control block number to -408. Okay. In the properties, we're going to leave the gain as 1.0, and we're going to set the target value at 0.458. Again, constant 2 is not necessarily used here, but if you want, you can also give it the same value, 0.458, for our target level. Okay, so now we have the calculated liquid level and our target level. We just have to create the error of that, or the level error. So simply just going to be subtracting the normalized level from the target level. So we're going to add in a subtraction control block. So go ahead and click on control block icon and find subtract, which is type 54 or number 54. Go ahead, enter that. And we can simply connect, we're going to connect our control block 406 to the plus side of the level error, or the control block 25. We're going to connect then the control block 408 to the minus side of our control block 25. And let's go ahead and change this control block number to 410. So we're going to call this minus 410. Okay, so that gives us our level error. Very simple, okay? The next thing we want to do is add in a function block that will take this level error as input and output the mass flow rate proportional to that error. Okay, we can do that by using a control block called a function block. So we again click on our control block, just click anywhere here to the right. Our function block is type 101/102. So find 101/102 function and input it. Okay, our function block takes one or more inputs. Here, we're going to first change our block number to minus 415. And if we look at the input right now, our function table is not disabled. We can't enter in a function table until we actually connect it to a hydraulic component. And or not a hydraulic component, a control block. So we're going to connect it to our control block 410 using our connection tool. Go ahead and click on the triangle to the right of our control block 410 and the first input of our function block 415. Now, if we go to the properties view of our function block 415, we can now see that we can enter in a function table. And this is where we're going to add in our values for our mass flow rate based on the level that we have. So we want to add another row. We just need 2 rows here. And the first input we're going to input is if the level's decreasing, so minus minus 0.1. We want, this is going to be for makeup flow. So if our level's decreasing, we want to add flow. So we're going to put in 55, represents 55 kilograms per second. That should be for the first block. Why is it not letting me enter it there? Okay, let's try this again. So minus 0.1, 55. We want to add another block. Okay. $55. We want our minus side there, and then our second row should be 0.0 and 0.0. So what trace will do is actually linearly interpolate between your points in your table and extrapolate. So here we're basically saying if it's dropping by 0.1, we want to add in 55 kilograms per second. And then if it's 0, we want it to be 0 and linearly interpolate between those points. Okay. So that adds in one function block, and that's going to drive our makeup flow. So we can actually click on our makeup flow fill here. And in the properties view under the state controllers, which is down towards the bottom of our properties, see that it's already connected to constant 23. We want to change that to our new control block minus 415. Okay, we click on minus 415, and you'll see now that your makeup flow is now connected to this function block and no longer connected to our constant. We need to do that same thing for the letdown flow, but our control block's gonna, our function table will be slightly different. So let's go ahead and copy that function block 415, and we'll do a paste special. And let's move that control block. It should now be numbered minus 416, which is what we want. Again, we want to connect it to control block 410. So using our connection tool, we connect it to 410 here. Now we need to change the function table values. We want it to change. Our first value here is going to be 0 and 0. Now for letdown flow, if the liquid level's increasing by 0.01, we want to remove 55 kilograms per second of inventory from our model. Okay, so once you've modified the function table, click OK. And now, again, we have to connect this to the letdown flow. So we can come into the letdown flow, and in the properties view, again, under the mixture flow controller, go ahead and locate 416, select OK. And now the model is complete. Again, it's a good thing to check the model to make sure that we don't have errors. So before we run this and test it, we're going to check model. We shouldn't see any errors. And then we can save our control system or our transient restart. Okay, now we're back to our steady state calculation. To run this calculation and examine the output to make sure that everything's working okay, we're going to go to the external restart file. Again, check to make sure that your trace executable is set up properly and pointing to the correct executable, that the animation model is selected. And if everything's okay there, we need to make sure that we're pointing to the correct restart file. So here we're going to restart this calculation from the steady state calculation that we just ran. So click on the restart file icon here in the restart file view. And then at the bottom where it says file, go ahead and click on the selection tool. And you're going to navigate to the PWR steady state calculation that we just ran. And then click on the PWR steady state TPR file. That's going to be our restart file for this calculation. Select OK. And now we're ready to run this restart calculation. Again, you can lock the view and hit the submit button. Another way to run a calculation, you can run it through the menu, or you can come over to the navigator window and click on PWR TR, right click on it and say submit stream to local. You ask to submit the stream, say yes. Again, your calculation should start and it should automatically connect to the animation. window. When you get the message that says resume or restart job, just say yes. And now you should see the calculation running. This is a very short calculation. It's only 175 seconds just to demonstrate whether or not our proportional controller is working properly. So this should run very, very quick. In the control systems plot, you should see two plots at the top of the screen that are showing you the normalized pressure level and then the makeup and letdown mass flow rates. In the normalized pressurizer level, you can see that the level is initially increasing, then decreases, comes to about a steady state, then decreases again and increases. And a lot of this behavior is caused by the transient calculation that's running. Here, we just want to see if our proportional controller is working properly. So our makeup and letdown flow should change proportional to this liquid level change. And when we look at the second plot here, makeup and letdown flow, we see that when the liquid level is increasing, the letdown flow is drawing off inventory. When the level decreases, then you see that below the target level, you see that the makeup flow kicks on and is on until, again, the level drops below or it starts to increase above that target level. And then, of course, letdown flow kicks on. So it looks like it's working properly. You should see results very similar to this if your controller's working properly. Okay, and that concludes this portion of the walkthrough. There's no questions. I'll turn over control to Lance to start the PI controller portion of this exercise.
If anyone does have a question, put it in the chat and we'll try to answer it there. We are running a little short on time here, so I want to make sure that we're kicking along to the next one. Also want to give people a chance to take a break if they need one. So let's just do a real short 2-minute break, and that'll give Lance time to kind of get set up, and then we'll resume.
All right, so this presentation will be talking about PI controllers in Trace with Snap. And so the intent of this part of the webinar is to gain an understanding of PI and PID controllers. And these are commonly used in models to reach steady state conditions. They're particularly useful when you're trying to reach multiple steady state conditions all at once, because the controllers can adjust the controls to target specific conditions concurrently. I know when I started, we would do that by hand, and it would take a long time to get it adjusted to the right conditions for your system. So we want to understand how to tune PI controllers for efficient control using a scaling approach. We'll also show you how to tune a controller using a Ziegler-Nichols method, and then we'll practice setting up PI controllers using these methods. So a typical control system, here for example, we have a faucet. Maybe you're washing your hands, and you want the temperature to be a good temperature for washing your hands, not too cold, not too hot. And so you turn on one of the handles, and then the second handle you're going to adjust to try and reach the temperature you would like. And so a control system is typically comprised of a signal, which would be the temperature or the liquid coming out. And then there would be an error signal, which would be essentially your hand kind of touching it to see whether it's the temperature that you like. And then there would be the difference, and the difference between the desired value and the actual value, the temperature coming out, would be your error. And then you would have a control parameter, which would be the faucet handle in this case, and control system, which would be your hand adjusting that system. So and The control system is designed to adjust the control parameter to drive the error to 0. So the control system responds to the error signal, and this acts on a feedback loop where you modify the controller, and this impacts the error, and then the error feeds back into the control system, which then can adjust the control, and so you have this loop. The control changing the error changing the control. And there's often a delay time before the error signal measures the response. For example, in this case, it could be the time for the water to go from the valve to the faucet exit where it can be sensed. With the controller, we're interested in achieving both stability and efficiency. So if a control is adjusted in the wrong direction, then it's going to diverge from the target value that we're interested in, and that would be unstable control. If the control parameters, if it's adjusted too quickly, you can overcorrect. And if you overcorrect significantly, the error signal can amplify and become unstable, which you can think of feedback through a microphone as an example. And if the parameter is adjusted slowly, then it's going to take a lot of time to get to the steady state. And you'd prefer that time to be efficient, get there quickly. So a common type of controller is the PID controller. And in this case, the control value is represented by Y. And then this would be the sum of a proportional control, so P times the error, an integral of the error times by another constant PI, and then the differential of the error, dE dt, times by another constant PD. And these three constants which characterize the controller are referred to as controller gains. And so the objective is to try and set these controller gains to give you a good control to get to the target value you would like. The system is very similar to the one we set up previously. We're going to have a target temperature, and this is just a constant block that says what target we're trying to achieve. Here we have a temperature signal, and then we'll subtract the two to get an error signal. And then we'll feed this error into an integration block, a differential block, and then directly into a sum as a proportional. And then we would be setting in this sum block a set of coefficients that could correspond to our PI constant, our P constant, and our PD constant that define the PID controller. So in a PID controller, one thing to note is the integral term. This term does not stop changing until the error goes to 0. This is not a characteristic of the proportional or the differential term. These terms can stop changing even when you haven't reached a value of 0. So it turns out that the integral term is required in order to make your error go to 0. The other two terms are there, and they're optional, but you almost always have at least a proportional term, and these are included to improve performance. So in a PID controller, the proportional term acts immediately. This one is your quickest effect to try and get back to towards a value of 0. So it has a benefit of rapid estimation. The integral term takes time to build up. You integrate over time, but the benefit of including an integral term is that it's refinement of your control, and this is the term that makes it go to 0 error. The differential term is a little more complicated to explain. The impact is a little less obvious, but it can counteract damping in a system, and it can help the system reach convergence faster, but it is also fairly sensitive to signal delay, and so it's most effective when there's little delay between your control and the signal. So the signal detects change right when it occurs rather than having some delay before it's detected. If the differential gain is set to 0, it's called a PI controller. And PI controllers do tend to be more common than PID controllers because they're simpler to tune for efficiency and they're less sensitive to signal delay. This presentation will primarily focus on PI controllers. We will have show a little bit of configuring a PID controller with the Ziegler-Nichols process that we show. So here's an example of a PI controller. It's constructed from a sum and integral blocks. So you construct your error signal as we showed below or before, with your input signal minus your target. And then that gets fed into an integral block, and then both the error itself and the integral get fed into a sum block, and that produces your PI controller once you've set gains within the sum block. There is also a PI control directly built in, and it has a bit different form. Our normal proportional integral controller has a proportional and an integral gain that directly multiply by the E and the E integral of E dt. For the PI controller, it actually uses this form where you have a proportional, like a P that gets multiplied by both terms, and then this 1 over tau value is a scaling factor for your time term. And so the inputs are slightly different, but they're compatible.
Lance,
Yes.
have you shared your screen? I'm not seeing anything on my screen, so maybe I'm doing something wrong.
Are others seeing my screen?
I see it.
Okay.
I see it.
Okay. That's interesting. I'm sorry, Jay.
Yeah, it happened to me also, but I leave the meeting and I get back in again, and it works now.
Okay, you might try that, Jay. Log off and log back in. So in the prior control systems, the error signal was defined by the target value minus the measured signal. In general, I actually prefer it the other way around. I like to do the target signal, or the signal minus the target, but you notice these have opposite signs. So these are both valid definitions of error, but they do have opposite sign, and this will be important later when we're determining gains, because the gains will actually be different between these two. The gains will be opposite. Like you'll have to flip the sign of the gains, and so this becomes important with our PI controllers later. And in this case, we're really going to use this E1 definition, the target minus the temperature, because this is what's used by PI and PID controllers built into trace. We wanted consistency. The other way does work. You just have to be aware you're going to have to flip the signs in your gains. So target, note that the target value used in the definition of error may differ in different simulations. So you're not always trying to reach the same target value. So for purposes of determining controller gains with the methods we're talking about, the target value really doesn't matter. You can set it to kind of whatever, and you'll be able to determine the gains still. So that's an error signal can be defined in your control system, even if you don't know what the target value is you're trying to reach. But another option is to directly use the signal without an error defined. And we'll note how to do this later with another caveat. So in order to have a valid control parameter, the changes in the control value must directly impact the steady state error signal. So there's got to be some relationship between if I change the control, it's going to change the error. But for a PID controller to work, it's not necessarily true for all types of controllers, but for a PID controller to work, there needs to be a monotonic relationship between Y and the steady state value of error over your control range. So in other words, there either needs to be an increase, a consistent increase in your error with Y, or a consistent decrease. If you get something where it goes up for a range and down for a range and up for a range, then a simple PI or PID controller is not going to work for the full range of control. The objective then is choosing gains of the control so that the controller is stable and efficient. So a stable controller is one that systematically converges on an error of 0. This requires controller coefficients or gains that have a correct sign and an appropriate magnitude. An efficient controller is one that has gains such that the system approaches 0 at close to an optimal rate. So in the representations of the controller we've represented previously, we haven't included the initial value of the controller. This is actually kind of convenient. It's useful to include at times. And it is actually part of the PI or PID controllers. You can add this, like for example, and if you're setting up the PI controller manually, you can add a constant block to set the initial value, or you can set an initial value on your integral block. You could also, there's an initial value constant you can use on your PI controller. In a lot of cases, the initial value is ignored because we just let the system adjust until the system comes into to an error of 0. And it will do that even if you haven't set the initial value, but it will be more efficient if you do set the initial value properly. So here's an example of when you've set your proportional and integral gains incorrectly. They're the wrong sign. And in this case, your error will tend to diverge from your target value of 0. And you can see it consistently diverging away. Now, if you do have the right signs, if it's the correct signs, but they're too large, then it will overcorrect, and you can see it oscillate about the equilibrium with growing amplitude. Now, if it's been properly tuned, then it should converge efficiently. If it's poorly tuned, then you'll see that the time it takes to reach your target value will be quite a bit longer. Now there's different methods you can use for tuning PI controllers. We'll discuss a couple. We'll talk about a scaling method that uses a step response technique to characterize your gains. We'll also use Ziegler-Nichols method and show you how to apply that. One thing to note is that precise gain values don't matter. Often when you're tuning, it's useful after you get an initial set of gains to adjust those to kind of tune your efficiency. Most of the time, the initial gains aren't going to be the most optimal. So it's useful to have quick estimations to get you in the ballpark, and then just make adjustments to your gains to push or move it towards a more efficient control. So we'll emphasize quick estimation over precise calculations in this presentation. Okay, so the scaling method. For the scaling method, we'll start with this form of the equation. We're going to have our control is equal to some initial control value plus this p gain, and then multiplied by our error plus 1 over tau, which is another gain, times by our integral of error dt. And this equation is written in terms of the error e, but for the scaling method, we want to scale the value of e so that it's an appropriate magnitude for our control variable y. And to do this, there needs to be a relationship between E and Y, our error and our control parameter Y. And we can estimate the slope relationship between these two. So here, if we've got this relationship between them, we can take the delta Y and the delta E and divide those, and that will allow us to establish a scaling relationship between E and Y. So the step response method is commonly used, and it's a simple approach to estimate this slope, delta Y over delta E. So we'll start with our system in steady state conditions. We'll apply a step response to our control. Sorry about that. I keep tapping the mouse. So we'll apply a step response to our control parameter, change it by a constant amount over a very short time period, and this will give us our delta Y. And then we'll look at the plot of our error signal and take the difference between where the error started and then where it ended. And this is our delta E, and from this we can calculate this relationship delta Y over delta E. So this is an example here of an error response. We change delta Y from 0.5 down to 0.1. And then we look at the response of the system. It changes from -2 up to a value of 1. So the delta Y is a value of minus 0.4, and the delta error is a value of 3. So our slope is about a negative 0.1333 repeating. Now, we can also use directly use the signal. Rather, we haven't defined the error signal. We just want to use the signal directly, and we can do this. In this case, we'll use the final value of our signal versus our initial value in lieu of the delta E that we talked about on the previous slide. However, we need to note that the definition of error determines the sign of this slope. So that the sign of the slope delta Y over delta E. Now, if our error definition is our target value minus our signal, then we're going to have a negative. We need to take the negative of the slope we calculate with just the signal, because we have a negative t here. If our definition of error is our signal minus the target, then the slope we calculate will be the same for error as it is for our delta Y over delta t. So, and this will be important for getting our gains right. So anyway, it's something you should note. It is often convenient to calculate things directly from the signal rather than the error, but you do have to be aware that your definition of the error will change how you treat this slope, the sign of it that you use. So we're going to do an exercise. I'm going to turn the time over to Isaac Hornbeck, who will cover an example of calculating this delta Y over delta E using a simple faucet model.
All right, thanks, Lance. So we're going to use the model that's labeled exercise 1 faucet MED. And if you want, you can follow along in the exercise instructions on the PDF called exercise 1 faucet step response PDF. So we're going to, like Lance said, try and calculate this slope for this system that we have here. To start off with, we're going to add a signal variable for our problem time. So if we come up here, control systems, signal variable, we can add a signal variable here. And we want it to be our problem time, which is this type number 0 here. So I'll just give it here and label this time just for clarity. Now what we want to do is send a signal to this faucet. We're going to control this hot water valve here. We want to send a signal to it. So we're going to add another control block right here. And this one is going to be a type function. So if we add it in, then we can filter here and find the type function, this 101, 102. Click OK. Now we have our function here. And before we can set the signal that we want to send, we have to connect our time signal to the function. So we can do that just with our connector tool. Now back in the function, we're going to set some data in this function table attribute. We can expand that there. So first, we're going to set at time 0, we're going to send a signal of 0 saying that our valve right here is going to be completely closed. Then we'll add another row. Let's see, before I do that, let me add there. So at time 0, we're going to have a signal of 0. Then at time 1.9, we're going to still send a value of 0. Then at time 2, we're going to send a value of 1/2. And then at time 30, which is the length that this simulation will run, we're going to keep it still at a value of 1/2.
Now, one thing to note, we kept it constant from 0 to 1.9. In your own models, you'd have to keep it constant long enough to reach a steady state. That's adequate for this model, but it wouldn't be maybe for a lot of plant models.
Right. There's another exercise that you'll be able to do that you end up having to do it at around 200 seconds so that it can reach a good steady state. So once you set these values, we'll click OK to save them. Now on our valve, we want to make sure that our valve type here is this flow area fraction. So that way it's expecting a signal with values between 0 and 1. Now we want to connect our valve to the function so that this function can control the valve. So in this attribute here, valve table independent variable, we're going to select the signal that we want, which is our function right here of number -1. So you can select that and click OK to connect it. Now that we have this whole thing set up, we're going to lock the model and run the simulation. So we'll want to make sure, as usual, that we have a valid trace executable selected. And then if you do, you can run the model. And just take a second here to run. Just bring this over here so we can watch the calculation for a second. And once it reaches 30 seconds, it finishes. And then now up here, we can select our plot files that we want to plot. You can select either one of these, whichever one you have. And this will open appplot. Okay, So what we're wanting to look at is the temperature of the water leaving the faucet. So if real fast we look back at this model, there's this pipe 31 here, and this cell 12 is the end of the pipe where the water is leaving. So if we come back to app plot, we can see in these data channels here are pipe 31, and the specific channel we want is called this TLN. You can see it's the liquid temperature that's in this pipe. And cell 12 is this last one. So if we select that and plot it, we can see that right at about 2 seconds when we changed our valve opening from 0 to 1/2, that it started to increase the temperature. And it increased from around 283-ish to about 314. So if we just come back here real quick, I have the note here we can check. Like Lance was talking about, to calculate the slope, this dy over dt, dE, we can use our signal, our temperature here, rather than the error, since in this plot here, this is our temperature signal rather than an error signal. So we're going to use this other method to calculate our slope. So our delta temperature is our final temperature minus initial, and we can just eyeball it on here. And from here to here, it's about 30 Kelvin. So we'll just take note of that value. And then we need our delta y, which if we look at our function that we set, we changed it from 0 to 1/2. So our delta y is, let's see, make sure I'm getting my signs right on it. So our delta y is the final minus initial, so it's 1/2 minus 0. So our delta y is a positive 1/2, and our temperature is the final minus initial. And if we check it again, it's this one minus this one, so it's a positive 30. Then if we come back here and plug these in, we have a 1/2 divided by 30, so we get about 1/60, and it's a negative value. Like Lance was saying, we need to make sure we get that sign right. So we have a minus 1/60. So we're going to remember this slope that we calculated, and we're going to use it in the next steps after Lance continues the discussion about these PI controllers.
And the reason it's a negative in this case is because the definition of error we're going to use is our target value minus the temperature signal. So that's why we're swapping the sign of this slope because of our choice of error.
Exactly.
Okay. Okay, thanks, Isaac. So getting back to our presentation, now that we have our relationship delta y over delta E, now we're going to replace the error value in our equation with a scaled error. So, so that we scale our error to the appropriate size for a control parameter. And we actually replace E by a negative delta y over delta E times E. And that applies for both our error and our integral of the error terms. And in this case, the minus sign here is not the same as what we talked about when we're using the target, when we're using, the signal to calculate our slope. This is actually the negative of delta y over delta E, not the delta y over delta T. So, and the reason we use a negative, it's this term acts somewhat like a spring constant, that if you're, or a spring force, that when you when you have a spring force in a mass spring equation, that spring force will pull back towards the equilibrium. It's the same concept here, that this term, we want it to pull back towards an error of 0. And so we're inserting a negative to get the proper sign for it to pull back towards the 0 error. And so in our equation here, we now have this new delta y over delta e, which scales our term here to be our error to be of an appropriate size for our control to get us back towards 0. Now the p, this p and this tau we haven't determined yet. These both need to be positive in this formulation. Now we're going to use to complete the scaling approach. We're going to use this heuristic equation below. So if we're given a current control value y0, if we're at this point and we want to go from this value, we want to make our control move back towards an error of 0, then the best estimate amount to step backward is to take to subtract delta y over delta e times by whatever our current, like our initial error is here. And this would step us, or it's our best estimate of how to get back to 0 error. Now, we'll apply this to the equation that we derived. So we'll set our heuristic equation here equal to our controller equation. And this suggests that this E0 has to be equal to this controller term right here for us to have properly scaled control. And so anyway, our proportional and our integral terms over time, they need to about approximate this error E0. So the first thing, looking at this equation for our scaling of the system, first of all, if we're just considering the proportional term, we'll ignore the integral term initially. Then if we ignore the integral term, then we'll let E equal E0, and our P value is just going to be 1. So that would be our controller, would be just P is a value of 1 and 1 times E. Now, if we let P equal 1 and then consider our integral term alone, then this becomes our scaling relationship. 1 over tau times the integral of E dt needs to equal our initial error. And so tau is a time scale value, and it needs to be positive. So in order to ensure that we get a positive value associated with each segment of our integral of error, then we're actually going to apply some absolute values to these values. So we're going to do the absolute value of the error times dt, and that's going to equal the absolute value of our initial error. And then we can calculate our time constant, our time gain here, by using one of the following equivalent expressions. So this came from our scaling relationship, and we can adjust it algebraically here to calculate our time value. And it's just going to be the integral of our error with time divided by the initial error. We'll divide out the error effect, and that'll just give us a time value. Or an equivalent way, a geometrical way to look at this is to multiply E0 by both sides so that we get this constant E0 times by this constant tau. And this rectangle needs to match the area under the curve for our area. And this is what we'll use, this geometrical approach is what we'll use for our estimation of tau. Okay, so here we have a plot of an error signal. We don't need necessarily the exact values. If we can get something that's close, it tends to be good enough. Then we can adjust our parameters from there as we look at the response of the system. But here we want to take this E0, this is our initial error, then we'll take E0 times by some tau value. We choose what that tau value is to try and get this rectangle to be equal to the area under this curve here. And so the blue area is shared by both. But we have this green area here now that needs to equal this area in order to have an appropriate tau value. So, so essentially we just need to pick that tau so that we get something that'll be close to where we get an appropriate time for this to match up with that integral. This provides a quick way to estimate just by looking at the graph rather than having to do an integral calculation. So here's another one. So here's one where we have oscillations that occur. And again, we're going to have our initial error, which is this value of 3. And then we'll form a rectangle by that value times by some tau value, such that this lighter blue area sums up to be equal to these darker blue areas that fall outside the rectangle. And it's just a guess. I mean, we might guess wrong. We can be off by a relatively significant amount and still have a pretty good value to use. So in this case, we've looked at it, it's probably about 6. Somewhere around 6 would be our tau value to apply. In the previous one, it looks like a value of maybe 1.9. I mean, you could even pick 2, that would be fine as your tau value. So you can also calculate tau directly from your signal rather than doing it from the error. And in this case, our tau value becomes our signal minus the final value of the signal, and then the initial error, the initial delta t is your t initial minus your t final, the absolute values of those. So in this case, we look and our difference in the ti minus tf is about 3. It's between 2. It goes from 2 up to 5. Our t final here is about 5, and so and then we can look at a value of tau where if we pick a value somewhere, it looks somewhere around maybe 4, or I don't know, maybe that's at 4.5 or something. That would give us an appropriate tau. So this rectangle is close to approximating the area under that curve. So all right, so our initial scale times that we came up with were p equal to 1 and tau equal to the integral of edt divided by our initial error. And we apply those now in this control equation. But these factors were determined using proportional integral terms independently. But when we combine them, then we've about doubled the error. So we're going to get about twice the error. And this is sometimes too aggressive, particularly with our proportional gain. And we may need to reduce the proportional gain and maybe even adjust our tau to get more efficient and stable control from these initial estimates. Now, the step response method estimates delta y over delta e. However, the underlying trend may be nonlinear. And if the slope varies significantly over this range, then the control parameter may be unstable in locations where the slope is small. So it could be unstable up here while it's stable down in this region. And in this case, it's useful to check the slope over multiple steps rather than just an individual step. And then choose the slope that's the smallest with the smallest absolute value if you want to have stability over the full range. And so that it can take a little bit more effort, particularly if you do an initial one, you try out the control system over different locations and you find it becomes unstable in some places. This is the PI block that comes in trace, and the values related to the items that we've been discussing are listed here. So the gain in the PI controller is our minus delta y over delta e term. That's typically where you would put this. And note that we do sometimes adjust this if it's too large. we might back off on this value. The constant target value, the target value is this constant 1 value. Constant 2 is our initial control value. So if you want to set the initial value of your controller, you can put that in your constant 2. The delta t, the thing labeled as delta t is our tau value, or our tau scaling factor. And then the constant time, this refers to a lag constant. We haven't really talked about lag. Lag can help get rid of noise, but it also tends to decrease the effectiveness of your controller if there is little noise in the signal. And then this final value at the bottom represents our input signal T. So now that we've talked about the process of configuring our controller, we'll have Isaac present applying the controller to this faucet example.
All right, thanks, Lance. So we're going to continue off with the same point in the model that we were at. If you weren't able to follow, there's a checkpoint model saved in the webinar materials if you'd like to start up from that one. So we had left off with, on that last exercise, of calculating this minus 1/60. And like Lance had talked about, that's not our gain value itself, but our gain value is going to be that minus delta y over delta e. So we take the negative of that slope that we calculated, and we'll just take note of it. It's about 0.017. Then we want to calculate or estimate that tau value, that delta t, that time constant that we want to know. So we're going to look back at that plot that we had plotted of our temperature signal. So our control signal changed at about 2 seconds right here. So we're going to just, for now, ignore anything between 0 and 2 seconds, since nothing was changing at that point. We're going to imagine creating that rectangle like Lance had talked about, where the area from this 2 seconds between this target value and this curve, so you kind of can imagine this being filled in right here, that area should be the same as the area of some rectangle that we draw right here. And
anybody want to hazard a guess of how big tau should be from that? How big would our tau be based on the discussion we had of the integral of this needs to be the same as our initial error times by some time amount?
Yeah, any guesses? Estimates?
It's like no guesses. Let's move on.
All right. So it seems that probably at about after maybe 2 seconds here, some rectangle about that large would probably contain all the area between that shape and the curve. So if we just kind of guess a tau value of about 2, that should be sufficient for this system here. So I'll take note of that value, and I'll just close this plot here. So our tau was 2, and we have our gain of 0.017. Now we're going to put in our PI controller block. So make sure our model is unlocked. And now we'll come up here to add from these control systems and a control block. We add it here. We want the type PI controller. You can see it's right here, this number 200. We'll add that type in. Now we need to feed into this PI controller the temperature of the water exiting this faucet. So we're going to add a signal variable. We come up here again and add a signal variable. We're going to add it in over here, and this one is going to be let's see, it's type 23, this liquid temperature. We're going to watch the temperature of the water exiting the faucet. We click OK to add that in. Now we'll connect our temperature to our PI controller using our connector tool.
See, did you configure the temperature to be the correct location?
Not yet. We need to
Okay,
do that. Thanks. So on our temperature signal here, if you select it, we can choose the signal that we want to get. So if we expand that, we get this selection menu, and we want to select our pipe 31. So if we open that, we have our pipe 31 right here. We can select that and click OK. And now again, we want the water exiting it, which is in the cell 12. So we're going to change this to cell 12. We click OK to save that. And now we see it's getting the signal from pipe 31. Now we don't just want to look at the temperature of the water coming out of the faucet. We want to see what our error is doing. So now that we have this, we're going to calculate our error. So we're going to add a new control block. This one is going to be the type constant. This is going to represent our target temperature that we want to reach. So we come in here, we can organize the type and look for the type constant, which is up here, number 9. We click OK to insert that. And I'll just label that one so that we can remember this is our target temperature that we're wanting to reach. In this case, we're going to choose a value of 310 Kelvin. So we'll set that in our constant 1 here. This will be the constant that's going to be output from this control block. Next, we want to calculate the difference between our signal and this target temperature, just how is done inside this PI controller block right here. So to do that, we need to add a subtract block. So you can do that again, add a new control block here. Select it here, and we want the type subtract. So again, we can sort type and find our type subtract, number 54. Then we can add that in. And I'll just label this as our error. So what we want to do is set our signal and our target temperatures into this subtract block here. And like Snap does in here, it's the target temperature minus the signal. So we can use our connector tool and select this output from the target, and we want it on the positive side. Then we select the output from our signal and put it on the minus side, our target minus our signal. So we connected there to get that, and now we have our error block set up. Now the last thing we need to do is just connect our PI controller to this valve so that it will control it. So you can select the valve and scroll down to our valve table independent variable. We can select from here, we want it to be our PI controller block number -2. So we can select that and click OK. Now we see we have our connection there connected properly. So now we'll save, lock our model, then we can execute it. We have a few values in our PI controller that I forgot to set. So we can go back here. Our PI controller, our gain value is this value that we calculated right here. So we'll just put in a 0.017 right there. Minimum and maximum are good to set if you know what values you can send from this to the component that you're trying to control. In this case, our minimum is 0 and our maximum is 1. We can only send values between that to this valve. Constant 1 is our, sorry, mixing things up. Constant 1 is our target temperature, which we chose a value of 310 Kelvin right here. So I'll enter that. Constant 2 is just that initial value. We can leave it at 0 right now. Our delta T is the tau value that we estimated, which we came up with about 2 seconds. So you can put in 2, and this time constant we don't need, so we can just put it at 0. So now we have all those values saved. Then we can come to our job stream and re-execute our model. And this time we're going to look at the value of this error block, this control block -4. Because we want to make sure that our error is going to 0. So if we open this again, it's running. Okay, so it's running our calculation. Once it's completed, we can view our plot files. Select that. And then again, like I said, our error was in control block 4. So it's under this control channel, and the CB4 is our control block 4. So if we select that value, this channel here, and click plot, we can see that our error does start up here close to 30, and it rapidly jumps towards 0, and then oscillates a little bit and relaxes pretty well towards 0. We can see it approach 0 there really good. So just like that, we can see that that PI controller did indeed bring our error towards 0, towards that target temperature of 310 Kelvin. And you can go in and choose some, just adjust your gain values, your tau value a little bit more to kind of fine tune that. You can actually get it to converge towards 0 closer to like 10 to 15 seconds even. And so that kind of concludes this exercise with the faucet model.
Lance, you're on mute.
There are some rules of thumb that you can use to diagnose issues with a PI controller. And these are only loose guidelines. They don't always work since dynamics can get complicated, but they can be helpful. It's useful to gain some kind of intuition. This hopefully it's intended to give some intuition about how the controllers tend to behave. But, all right, so if you see significant oscillation about 0, this is an indication that your integral gains is too large, or that the time scale, your time scale tau, is too small. And this can lead to an integral term that's overcorrecting and shooting past the target value. And it is one characteristic of the integral term that it will always oscillate about 0 if that's a problem, if it's too large. Now, if you see an oscillation, but it doesn't necessarily center around 0, this is also an indication your gains are too large, but this points to your proportional gain being too large, and that you need to back off on the proportional gain. Now, if they are centered around 0, proportional gain can make that happen as well. So it's you sometimes have to adjust both independently to kind of see what brings you more into line. But if it's not centered around 0 or is biased significantly away from that, it's a pretty good sign. It's not your integral as much as your proportional. Now, if the convergence does not cross the target value, this is often, but it's not always, a sign that the gains are too low and could be increased for more efficient control. And then if you see some sort of a significant kink or change in slope after the initial response, this indicates an imbalance between your gains. Like your proportional gain may be okay, but your integral gain is too low and needs to be adjusted. Often the control looks a lot more smooth when the two are balanced properly. Then convergence with slight oscillations is common for efficient controllers. You can often get rid of, often get at the point where there's really no oscillation except for a quick bounce back to the equilibrium with a really efficient controller. But this is usually, it's a good sign usually if it looks somewhat like that. Do we want to do the poor tuning examples, or maybe we should move on to Ziegler-Nichols? I think we.
Yeah, I was going
Yeah, I
to
think we can
suggest
move on.
let's move on. Yeah.
Okay. So Ziegler-Nichols is another relatively simple tuning technique for PI controllers. Applying the step response technique first to estimate your initial gain P as this negative y over delta E is a useful step. Like if you want to know where to start with Ziegler-Nichols, it's very helpful. Ziegler-Nichols is not as robust as the scaling method, and there's cases where it doesn't work, but it can be a quick way of getting a reasonably efficient controller, so it's worth knowing. The Ziegler-Nichols method steps are fairly simple. We set an integral gain to 0. Then, starting from stable conditions, we increase our proportional gain until the system oscillates with fixed amplitude oscillations. This will be called our Pmax. And then from the error response, this oscillatory response will take the oscillation time period, which will be this TP value, and then we just adjust our control values based on this table. For just a P controller, which isn't going to get you isn't likely to get you to a target of 0, you would just use half the Pmax. For a PI controller, you can use this 0.45 Pmax times 1.2 Pmax divided by TP. And then for the PID controller, you use the coefficients defined here. And this often gives you good control with a relatively limited effort. one thing to note is that the Pmax should be, one thing too, before we've been doing the PI controller, which doesn't use a PI term, it uses a tau term. The equivalent of setting PI to 0 is just put a very large value for tau, or for that constant for the delta t. Just set that to a very large value, so this is about 0. Note that Pmax should be proportional to the proportional gain when stable oscillations first start. So sometimes you might put in a value and it's already oscillating, and you can have it oscillate stably over several orders of magnitude. So you really need it when it starts to oscillate. And so if it's already oscillating when you put in a p value, you need to back off until it starts to decay, the oscillations start to decrease down to an equilibrium. And then from there you can increase to get the Pmax that's at the start of the unstable region. And so that needs to be done before applying the Ziegler-Nichols coefficients. We'll now move on to, we have Jack Haney, which will present the Ziegler-Nichols method with this this controller or this faucet example to show how that's applied.
All right, thank you. So if you want to follow along, we have instructions here. This is available in PDF form. And then if you want to open up your the models, exercise 4, there's 2 exercise 4s. One is an animation file, and one's just the model file. We see that I constructed here a PI controller sort of by hand with control and signal variables. I allowed the proportional gain, integral gain, and target temperature to be interactable variables so that we can interact with them as the animation plays out. So in order to submit the job, you make sure this is locked. Go to execute faucet. And as the calculation starts, the animation will also open up. One little trick I found is to fast forward there and then to click play twice and then resume calculation. That just makes it so that the animation plays at the same exact time that the calculation is calculating. That way, when you enter proportional gains, you'll see them activate here on the plot immediately. So yeah, with Ziegler-Nichols, it is kind of hard to determine what order of magnitude is correct to start at. Because we did the step method, we know that it's, roughly on the order of 1/100th or 1/60th rather. But if you didn't know that, then you might just start with 1 and you'd see that it's oscillating at roughly constant amplitude. So you know that that's potentially too high. You want to find like the lowest value that it's unstable at, like this. So you might try 1/10. You still see that it's not decreasing, it's not stable. 1/100th. Now you see that it's stable. And then you might start increasing so that you get like one of the first values that it's unstable at. So instead of 1/100th, we might try 2/100ths. Stable again. 3/100ths. Now it's starting to get unstable. So then we can decrease it a bit. I just happen to know that 26 thousandths is a good number. As 25 thousandths, I'll show you here, it begins to just barely be stable, and this amplitude of oscillation begins to decrease until it flattens out. So that's how you find that GP max, that max gain is of 0.026 0.06. And then Ziegler-Nichols, that method tells you to multiply that value by 0.45, which is roughly 0.0117. And then we can restart just to look at this plot. Once again, to note the period of oscillation that we see in the plot. So we'll skip ahead again, hit play twice, and then reset it to 0.026. And we see that this is roughly from here to here. It's roughly about 10 seconds, maybe a little bit less, like 9 seconds. So we'll take note of that as well. And the integral gain will be set to 1.2 times that max gain, and then divided by the period of oscillation. So that's 1.2 times 0.026 divided by 9 seconds, which is roughly 0.00347. So we can actually, you can open the checkpoint Ziegler-Nichols model, which is in the checkpoints folder here. Or I could show you also how to just set those as initial starting values here. So in constant 1 of the proportional gain controller block, you can put in 0.0117. In the integral gain, you can put in the integral value 0.00347. And then go to your job stream, click execute faucet again, and we'll see how that responds. So you see that it levels out pretty quickly. We're watching the integral integrate. And you'll notice that it slows down the rate of change of the integral. So that means it's really, really close to 0. And actually have on the exercise that you can, I allowed you to change the target temperature, but then you'll note that the integral doesn't naturally reset when you change the target temperature, which is a problem, because then your response is offset by an integral. And say you're messing around with this with different proportional gains and your integral was like really large because it had just been off for quite some time from 0. So say it was like 3000. You change your target temperature, but your it doesn't respond to the proportional gain because the integral gain has completely dominated the signal. So I put in a script that resets the integral whenever you change the target temperature so that you can see the response. The reason I put this in is because you might think that it is still a good, oh, I need to skip ahead. You might think that it's still a good PI controller for, say, 315 Kelvin. But you see that it's actually very, if you imagine this as a harmonic oscillator, it's very overdamped. And it takes a long time to get back to 0 error. And then if you, say, try 300, which is lower than our initial target temperature, 310, then it's underdamped. And it's just oscillating a lot. It takes a long time to get back to 0 again. And this is because of something that Lance talked about at the very beginning of his presentation, which is that there's a theoretical curve that we never really plotted or talked about much, but it's that the signal or the controller, you can think of it as a function of the error. And what we're setting the proportional controller roughly to in the same order of magnitude of is the derivative of that, or the slope of that curve. And that's actually what I put in the exercise instructions at the very end. I put a note of that, and then I gave an approximation of that curve, where you see the control parameter here, which is the valve valve flow fraction, being fluctuated from 0 to 1, and then you see what the target temperature is here that it approaches. And then you can take the derivative of this to find roughly the max proportional gain as a function of temperature. So you see that your proportional gain has to get much more aggressive as the target temperature increases closer and closer to about 318, which is what you get when you take the average of the two faucet handles temperatures, and then much less aggressive when you have a decreased target temperature. But yeah, so that's how Ziegler-Nichols works. It's nice because it's completely empirical, so there's not a whole lot of analysis or computation that needs to happen beforehand. But it just does take a little bit of time to get the right max proportional gain, especially if you don't have an easily adjusted model like this one. Thanks, that's pretty much it.
Well, so that's it for our PI controller presentation. So in essence, the big challenge with PI controllers is figuring out what the proportional and the integral gain should be. We provided some ways of estimating what those are. The negative of delta Y over delta E, or is a good estimate for proportional, get you in the ballpark. And for the tau value, for the inverse of, well, for the tau value, as we showed in our equations, it's using the integral of the error divided by the initial error. It gives you a reasonable time value to use to scale your process, or set your gains. And it's that often that's the hardest part, is trying to get yourself into the right ballpark. That's been challenging for a lot of people who've done PI controllers, and this provides a simple way to do that. Do we have any questions as we finish up our presentation?
Yeah, we don't have time. I see Jace4 added to the chat, just an example of the input for using the generic signal variable. We don't really have time to go into that now. We can save that.
I can run through it real quick if you want, Doug. I have
just
one
real
set up
fast, and
already.
then we're
real
a little
fast.
over.
I have it set up.
All right, go ahead.
Okay. So yeah, if you want to use the generic signal variable, I just did a quick example. So if we wanted to grab this pressure in cell 16 using it instead of the pressure signal variable, we can insert a generic signal variable into our model. And you can see that, again, you can name it, you can give it your unique ID, but the three main inputs are down here. The general signal represents the component number. So ours was pipe 105, so we're going to input that. The variable name is an ASCII text string that represents the parameter you want to plot. In our case, we want to plot pressure, so PN, or get PN, not necessarily plot it. To get through some input processors, all of these variables need to be preceded by LU. So if you want something else like the velocity of the liquid, so VLN, it would be LU VLN instead of LUP in here. And then finally, the location is the cell of the variable that you want. So the cell location. So for ours, this would be how we can get the pressure. And I ran a quick steady state calculation and plotted our signal variable 21 versus our new generic signal variable here. If I replay this animation, you can see that they both overlap with each other. So that's one example of how to use the generic signal variable. But you can get other things, like I've used it to get cell width, so dx, and other parameters from the models.
And it does require knowledge of the actual variable name in Trace and the Fortran source code of Trace. And that information is not available in the distribution packages we send out with Trace. We can certainly add that in the future. And if anybody would like to request it, we can put something together and have that available to you, so you know what variables you can actually pull from in Trace. And these would extend, the purpose of using the generic signal variables to extend beyond the plottable variables that you have or the accessible variables you have, and get into maybe a little bit more detail if you need specific quantities for correlations and things like that. So, and so if anybody's interested, reach out to us after this meeting and we can make that available to you.
One of the challenges, it does present challenges too, because the location is not, there's complications in how the location is interpreted, and it can be there. You do have to understand some details of what's happening in code to get the right variables a lot of times.
That is also true. And also when the variables get updated, you have to be cognizant of that as well throughout the time step. So with that though, I did want to also mention that as part of the packet of information you received for this webinar, you did receive all the exercises. And so I do encourage you to go back and look at that exercise 3, for example. That's a good one to walk through in terms of understanding how you can achieve POR gains, proportional interval gains, and what the results might look like. So it's an exercise that allows you to play around with POR gains and see the effects of it. So I encourage you to do that. Also, there's a full plant model exercise for controlling your gains as well, and because you're going to get a little bit different response in a full plant model versus just these small faucet problems we were looking at. And so I encourage you to look at that exercise 5 as well in your free time and become familiar with the responses that you would typically see when trying to use a PI controller. And I'll just give a personal note here. I know when I was first starting out, learning how to do trace analysis, and trying to work with controllers, it was a nightmare. I was just stabbing in the dark and trying to find, good proportional interval gains. And so using these methods really do help. And I encourage you to familiarize yourself with them if you're not already, and become really good at either the step response, the scaling method, or looking at Ziegler-Nichols. Both of them will help you achieve a good, efficient controller in a relatively short amount of time, and you won't just be stabbing in the dark. All those cases that Lance was talking about with poor proportional and interval gains, I've dealt with all of them in my experience, and maybe you have too. So hopefully this has been helpful to you. I guess with that, Chris, did you have anything else you would like to say to close us out?
No. No, thank you everyone for, showing up. That's all.
Okay, thank you, Chris. And again, we will make the recordings and the presentation materials, the webinar materials available on NRC Codes as well for anybody else if you would like to provide the links to, and they can have access and run through the exercises themselves as well. So with that, we thank you, and we'll look forward to seeing you at the next Trace webinar, probably sometime around mid-late July. Thank you, everyone.